This is problem set number 5, problem 4. Two identical spheres with mass m are hung from silk threads of length L is shown. Each sphere has the same charge, so Q1 equals Q2, which we'll just call Q. The radius of each sphere is very small compared to the distance between the spheres, so they may be treated as point charges. Show that if the angle theta is small, the equilibrium separation d between the spheres is given by d equals q squared times L divided by 2 pi epsilon naught mass times gravity to the power of 1 over 3. Hint, if theta is small, then tangent of theta is basically sine theta. Okay. So we are given a mass of m and a charge of Q1 equals Q2, which we just call Q. Okay. So let's get started. Oh, also, this hint of if theta is smaller than tangent of theta is sine theta, that's basically saying, to pretend that's a triangle, this is a right angle, this is theta, and so we've got SOHCAHTOA, right? And say this is, let's call this side adjacent. So let's say side A. This is side O for opposite, and this is side H for hypotenuse. It's saying that if theta gets smaller, so now this is H, and if it gets even smaller than that, so this is now H and this is now theta, the tangent theta is equal to sine theta, or that the ratio between the opposite side over the adjacent side is going to be pretty much the same as the opposite side over the hypotenuse, right? Because as theta gets smaller, H becomes almost the same length as A. So that's all that hint is saying. So let's go back to the problem. Okay, so first I'm going to draw a free body diagram. Oops. Mark my coordinates, x and y, right? And I've got my y there. And my x there. Okay, so this is y, this is x. And because these are symmetrical, I'm just going to use one point. So let's say I choose this point right here for point Q. So over here I've got Q, right? The charge Q. That's sphere. So I'm going to have what forces? I'm going to have tension that goes this way. I'm going to have mass times gravity that points down this way. So mg tension. And what else do I have? I also have the electrostatic force going this way, which comes from the other charge Q towards my left, right? Because they're both, they have the same charge. It's going to repel me. It's going to repel this guy towards the right. So this is my electrostatic force. All right. So I'm going to break this tension force down into x and y components. Right? So let's say if we call this angle theta. Right? My tension component along x would be t sine theta, right? And along y, right here, this would be t cosine theta. Okay? And I know this angle is theta because if I drew my y-axis there and my x-axis there, and this was theta, then this is also theta, right? Okay, so now for step one, I'm gonna write a summation of forces along x. So I'm gonna have that my electrostatic force, which is positive since it's pointing towards positive x, minus my tension sine t sine theta, or the x component of my tension force, right? And it's minus because if you look at where tension is pointing, at least the x component, it's pointing towards negative x, right? So that equals 0. Therefore, my electrostatic force is going to be equal to my x component of tension, t sine theta. All right? And what's another way of writing electrostatic force? That would be Fe, the magnitude of Fe, is equal to K, or the electrostatic constant, times Q1, the source charge, times Q2, which is the charge where we're feeling this force, divided by r squared, where r is the distance between the center of the two charges, okay? And again, K, the electrostatic constant, is just equal to 1 over 4 pi times epsilon naught, where epsilon naught stands for the permittivity of free space, or how well the electric field works in a vacuum, okay? So using that information, I'm going to substitute Fe for K times Q, which, as stated here, Q1 is equal to Q2, which is just equal to Q, so then that just becomes Q squared over D squared, right? Because that's the distance between the two charges. That's this guy right here. This is D. So D is going to be our R, but in the formula we have to square that, so this is now D squared equals to T sine theta, or the x component of tension. Okay? And step 2, I'm going to write the summation of my forces along y, along the y component, or the y component of forces. So Fy, that will be what's positive, that's going to be the y component of my tension, so T cosine theta, minus, since the weight is pointing towards negative y, so minus mg equals 0, right? So then my tension cosine theta equals mass times gravity, and tension will equal mass times gravity divided by cosine of theta, okay? So now that I know my tension in terms of my mass, my gravity, and theta, I'm going to substitute that for the equation I got in step 1 right here, okay? So step 3, I'm just going to rewrite this equation and substitute t for mg over cosine theta. So that's going to be k q squared over d squared equals mg over cosine theta times sine theta, right? So I just substituted t with mg cosine theta since I solved that in step 2. Okay. Again, what is sine theta over cosine theta? That's just tangent theta, right? So I'm going to rewrite that as this is equal to mg tangent of theta. mg times tangent of theta. So again, using the hint that we talked about earlier where tangent of theta is basically equal to sine theta, I'm just going to substitute that by saying that is now equal to mg sine of theta, okay? Using the hint. So from the hint provided, I just substitute tangent of theta with sine of theta. And again, if you don't know how, if you need an explanation of why when theta becomes very small, tangent of theta is essentially equal to sine of theta, I did provide that explanation right at the beginning of the video, so you can just rewind and watch that again. Okay, so now using geometry, what is sine of theta? Right, so let's go back to our problem right here. Actually, I'll move this down. I'll copy this. And I'll paste it here. But actually, all I want is this, so I'll just move that along there. Okay. Okay, what is sine theta? Again, if I just want to look at, right now, I want to look at this triangle right here. Oops. This is a right triangle, right? This angle is theta. And it was provided in the problem actually that the distance between the two charges was d. So if that's d, then I know that this distance for this angle is d over 2, d divided by 2, since both these angles are theta, right? Okay, and then this hypotenuse is of length L. So I know I can find my sine of theta, right? Using SOHCAHTOA, sine is opposite over hypotenuse, right? So now this is equal to mg times what is the opposite? It is opposite side of theta is d over 2. So d over 2 divided by the hypotenuse, which is L, okay? Okay, so now that I've got that far, I'll just bring this down here. So now that's kq squared over d squared, right? And I'm trying to solve for d. So then that will be kq squared over d squared is equal to mg d over 2L, right? And I'm gonna cross multiply, so kq squared times 2L is equal to mg d cubed. Okay? And I am going to plug in, remember, k, the value for k, the electrostatic constant is just 1 over 4 pi epsilon naught. So I'm just going to substitute that in for k. So q squared 2L over 4 pi epsilon naught is equal to mg d cubed. So then d cubed is equal to q squared 2L over 4 pi epsilon naught times mg. Right? So then d is equal to q squared 2L over, actually, before I get there, I could actually cancel out this 2 and this 4, so this becomes 2. So my d would be q squared L divided by 2 pi epsilon naught times mg to the power of 1/3. Okay? And so that is our final answer for problem number 4. Not too bad.